Welcome to the deep dive. Today we're focusing on something absolutely crucial if you're aiming for a senior level software engineering role, especially when those technical interviews come around, message brokers.
Mm,
We're going to really dig into the difference between message queues and topics. On the surface, it might seem simple, but truly understanding their strengths, weaknesses, and when to use each is, a hallmark of a seasoned engineer.
absolutely.
Our goal today is to make sure you can clearly articulate the distinctions, explain their ideal use cases, and highlight the key considerations when you're dealing with message brokers. Plus, we'll break down how they enable asynchronous communication and why that's such a game changer.
Exactly. For anyone preparing to step into a senior role, demonstrating a solid grasp of distributed systems concepts like message brokers is, well, it's vital. Interviewers aren't just looking for definitions. They want to see if you can apply these ideas to solve real-world problems and discuss the trade-offs involved.
Right, the practical application.
Yeah.
So let's get started. Okay, let's unpack this. At their heart, message brokers act as go-betweens, like a sophisticated internal messaging system for your applications. In modern architectures, particularly with microservices, they're often the engine for asynchronous communication.
Yeah, that's a good way to put it.
Instead of services directly calling each other and waiting for a response, they send messages to the broker, essentially saying, hey, here's this information. Please make sure it gets where it needs to go.
That's a great analogy. It really highlights the decoupling aspect. A service sending a message doesn't need to know the intimate details of the receiving service, its location, its current state.
Right.
It just needs to be able to communicate with the broker. And these messages can be anything. A command to do something, a confirmation that something happened, or simply an event announcing a change in state.
So let's get into the specifics that someone interviewing for a senior role really needs to nail down. What exactly is a queue in the context of message brokers?
Okay, think of a queue as a direct one-to-one communication channel, although it often involves groups. Imagine a line where messages are added at one end, and one of the available consumers picks it up from the other.
Okay.
The crucial concept here is the consumer group. You might have multiple instances of a service, all designed to handle the same type of message, and they all act as a single logical consumer by belonging to the same group.
Right. So if we have, say, 3 instances of an inventory updater service, and they're all part of the same consumer group subscribed to an incoming orders queue, what happens when a new order message arrives?
Only one of those 3 inventory updater instances will receive that specific incoming orders message. The broker ensures that each message on the queue is delivered to exactly one member of that consumer group.
Ah, okay. So it's load balancing, essentially.
Exactly. This is a key pattern for distributing workload. It's the idea of competing consumers. You have several workers ready to process tasks from the queue, preventing any single instance from being overwhelmed during peak loads. This is a common way to achieve scalability and resilience.
That makes perfect sense. It's like having multiple workers handling tasks from a central to-do list, with each task only being picked up by one worker. Now, how does a topic differ from this, and why would you choose it over a queue?
Topics take a fundamentally different approach: broadcast. Instead of a single consumer group receiving a message, a topic allows multiple independent consumer groups to subscribe and each receive a copy of the same message.
By copy, okay.
It's more like publishing a notification. Anyone who has subscribed to that particular topic will get a notification, potentially.
So let's say our order processing service now publishes an order shipped event to an order events topic. What happens then to the other parts of the system that might be interested in that event?
Okay, good example. If you have a shipping notification service group, perhaps with multiple instances to handle the volume, and an analytics dashboard service group, also with its own instances,
Right.
and both of these groups are subscribed to the order events topic, then both groups will receive a copy of that order shipped event.
Both get it.
Yes. Importantly, within each group, the broker will typically ensure that only one instance processes a given message. So one instance in the shipping notification group will handle sending the confirmation, and one instance in the analytics group will process it for reporting.
Okay, I see the key difference. The queue is about getting a task done by one of the available workers, like a shared workload, while the topic is about letting multiple interested parties know that something has happened. So the shipping service can do its job, and the analytics can update their dashboards, all triggered by the same order shipped event,
Exactly.
without them needing to know anything about each other beforehand.
Precisely. This loose coupling is a major advantage of using topics, especially in event-driven architectures. Different parts of your system can react independently to the same events, making the overall system more resilient and easier to evolve. You can add new services that subscribe to existing topics without needing to modify the services that are publishing those events.
Now, someone preparing for a senior interview might be asked about the nuances. At first glance, it might seem like a queue with just one consumer group behaves a lot like a topic, right?
Yeah.
What's the core distinction that an interviewer would be looking for?
That's a very astute observation, and yeah, it highlights a key understanding. With a queue, there's an implicit awareness on the part of the sender about the type of processing that needs to happen. They are putting a message onto a specific queue, expecting a service or a group of services designed to handle those messages to pick it up.
They know the intent.
Kind of, yeah. With a topic, the publisher broadcasts this event without necessarily knowing who or even how many subscribers there are. The focus is on announcing a fact or a state change. This happened, not do this specific thing.
So if the interviewer asks when to use which, a good rule of thumb would be that if I need a specific action to be taken and completed by one of the available workers, a queue is the way to go, command-like.
Yep.
But if I need to announce that something has occurred and multiple independent systems might need to react, then a topic is more appropriate, event-like.
That's a solid, concise way to put it. Queues are often used for commands or tasks that need to be executed exactly once by a worker. Topics excel in scenarios where you have broadcast needs, allowing for decoupled, event-driven interactions.
Okay, so we've got a good handle on the difference between queues and topics, but let's zoom out a bit. Why should a system even use a message broker in the first place? What are the core benefits that make them such a fundamental part of modern distributed systems, and what should I emphasize in an interview?
Okay. The most fundamental benefit, and one that senior engineers should absolutely understand, is the concept of guaranteed delivery.
Guaranteed delivery, right.
Reputable message brokers are designed to ensure that once a message is accepted, it will eventually be delivered to its intended recipients, even if there are temporary failures in the receiving services or, network issues.
So if I'm a service sending a critical message, I don't have to constantly worry about whether the downstream service is currently up and running. This sounds like it significantly improves reliability.
Precisely. If a receiving service is temporarily offline or overloaded, the broker will hold on to the message until the service becomes available and can process it. This takes a huge burden off the sending service.
Yeah, I could see that.
Compare this to making a direct synchronous API call like HTTP. If the receiving service is down, the sending service has to handle the failure, implement complex retry logic, potentially queue requests itself, and deal with the uncertainty of whether the operation eventually succeeded.
Right, you're pushing that complexity onto every sender.
Exactly. Message brokers abstract away much of this complexity.
That sounds like a major win for building resilient systems. How do brokers actually achieve this guaranteed delivery? What are the underlying mechanisms I should be aware of?
Well, they typically rely on durable storage. Messages are written to disk, usually. This ensures that even if the broker itself experiences a temporary outage or needs to restart, the messages are not lost.
Persistent storage. Okay.
Furthermore, most production-grade message brokers are designed to be deployed in a clustered configuration. This means multiple broker instances work together, providing redundancy. If one instance fails, the others can continue to operate, preventing a single point of failure and ensuring message delivery.
That makes sense. So the combination of persistent storage and clustering is key to this guarantee. But I remember reading that there can be complexities involved in setting this up correctly. What are some of the potential pitfalls or things to be careful about?
You're right, it's not just plug and play for high reliability. Running a message broker reliably, especially in a clustered environment, requires careful configuration and monitoring. Factors like network latency between the broker nodes, proper disk I/O performance, and understanding the broker's specific consistency model are crucial.
So the details matter.
Immensely. Misconfigurations in these areas can indeed compromise the guarantee of delivery. For example, some brokers, like RabbitMQ in certain cluster modes, have very specific network requirements, like low latency for their clusters to maintain quorum and prevent data loss during failures. So as anyone preparing for a senior role should know, simply deploying a broker isn't enough. You need to understand its operational requirements thoroughly. Read the docs.
Read the docs. Good advice. And I've also heard that the definition of guaranteed delivery isn't always absolute and can vary slightly between different brokers. Is that something I should be prepared to discuss?
Absolutely. Different brokers might offer different levels of guarantees and have different failure scenarios they can handle. For instance, many guarantee at least once delivery.
At least once,
Yeah.
meaning potential duplicates.
Meaning a message might be delivered more than once in rare failure scenarios, but it won't be lost. Others might aim for exactly once delivery, which is, frankly, a much more complex undertaking in a distributed system.
Okay.
Understanding these nuances and the specific guarantees offered by the broker you're using is vital. Ultimately, you are placing trust in the broker's reliability and, importantly, the operational practices surrounding it.
Right, it's not magic. Beyond just guaranteed delivery, what other valuable characteristics do message brokers often bring to the table that a senior engineer should appreciate?
Several useful ones. Message ordering is a significant one. Many brokers can ensure that messages are delivered to consumers in the same sequence they were sent, at least under certain conditions.
That sounds crucial for some applications.
It is, especially where the order of events matters, like processing financial transactions or state updates. However, it's important to note that this isn't always a universal guarantee across all messages or consumers. Sometimes ordering is only guaranteed within a specific partition of a topic or queue, like in Kafka.
Ah, partitioning affects ordering.
Correct. Therefore, as a consumer, you should sometimes be prepared to handle situations where messages might arrive out of order, or at least understand the precise scope of the ordering guarantee provided by your specific broker and configuration. Don't just assume strict FIFO everywhere.
That's a good point about not taking ordering for granted. What about ensuring that a message is processed only a single time, even if there are retries or redeliveries? You mentioned duplicates with at least once.
Right. That leads us back to the complex but important concept of exactly once delivery. As we touched on, standard guaranteed delivery, especially at least once, can sometimes lead to messages being redelivered, particularly if there's a failure after delivery but before processing is fully acknowledged. This can result in a consumer processing the same message multiple times, which can have undesirable side effects, like charging a credit card twice.
Definitely undesirable.
Yeah. While brokers are constantly evolving to improve exactly once semantics, it's often considered a very challenging problem in distributed systems. There are debates about whether true exactly once delivery is even possible versus exactly once processing.
So even if a broker offers features aimed at exactly once delivery, what's the recommended approach for consumers to handle potential duplicates? Just in case.
A best practice, and something interviewers will definitely look favorably upon, is to design your consumers to be idempotent.
Idempotent,
Meaning that processing the same message multiple times has the exact same outcome as processing it only once. A common technique for achieving this is by including a unique identifier in each message and having the consumer track which IDs it has already successfully processed, maybe in a database or cache. If it receives a message with an ID it has seen before, it can simply acknowledge it and ignore it, preventing duplicate processing effects.
Got it. Track message IDs. That seems like a robust strategy.
Hmm.
You also mentioned transactions earlier. How can those be beneficial in maintaining data consistency with brokers?
Right. Some advanced brokers offer transactional capabilities. This might involve write transactions, like allowing you to publish messages to multiple topics or partitions as a single atomic unit within the broker.
Okay.
Or, perhaps more commonly discussed, coordinating broker operations with external systems, like a database. The idea is to ensure that either all related operations succeed, for example, update database and publish message, or none of them do, preventing inconsistencies. For example, you want to ensure an order is only marked processed in your database if the corresponding order processed message is successfully sent via the broker. Transactions, often using patterns like the transactional outbox, can help guarantee this.
So ensuring atomicity across systems.
Essentially, yes. And some brokers also offer read transactionality, ensuring a message isn't fully removed from the queue until the consumer signals successful processing, tying into that at least once or exactly once processing goal.
It sounds like there's a rich set of features available depending on the message broker chosen. When it comes to making that choice, what are some of the popular options that a senior engineer should probably be familiar with, and what are their general strengths?
Yeah, there are indeed many options, each with its own trade-offs. Popular open source choices include RabbitMQ.
Heard of that one.
Yeah, known for its flexible routing capabilities using AMQP and generally considered relatively easy to use. Then there's ActiveMQ, another mature and widely adopted broker, part of the Apache ecosystem, and Kafka, which we should definitely talk more about.
Yeah, Kafka seems to come up a lot.
It does. It's known for its high throughput and fault-tolerant design, particularly well-suited for stream processing. Then you have the cloud-managed services, which are super common now. AWS SQS Simple Queue
A
Service.
class.
A real classic, yeah, highly scalable and fully managed queue service. AWS SNS Simple Notification Service, which is more for pub sub messaging like topics, and AWS Kinesis, designed specifically for real-time data streaming at potentially massive scale. Other clouds have similar offerings, of course.
Okay, lots of choices. You mentioned Kafka a couple of times now. It definitely seems to be a hot topic, especially in the context of large-scale data processing. What makes it so notable, and why should someone interviewing for a senior role understand its key characteristics?
Kafka has gained tremendous traction in recent years, yeah, particularly for building high-performance data pipelines, enabling real-time analytics, and supporting event-driven microservices at scale. Its architecture was specifically designed from the ground up to handle massive volumes of data, think trillions of messages per day, with low latency and high fault tolerance. It originated at LinkedIn to solve their, frankly, enormous data handling challenges and has since become a cornerstone of many large-scale systems.
So it's really built for handling serious scale and high throughput. That's something I should definitely highlight if it comes up in an interview, especially if discussing large systems.
Absolutely. Kafka's design, with its partitioning strategy and distributed commit log structure, allows it to scale horizontally pretty effectively. It can handle a huge number of producers writing data and consumers reading data concurrently, often within a single cluster. While not every company operates at LinkedIn's scale, Kafka's ability to scale makes it an attractive choice for organizations anticipating significant growth in their data volumes or messaging needs.
One of the unique aspects I've heard about Kafka is its concept of message permanence or retention. Could you explain why that's significant and how it differs from more traditional message queues?
Yes, that's a really key differentiator. In many traditional message brokers, once a message has been successfully processed and acknowledged by all relevant consumers, it's typically deleted from the broker to save space.
Right, it's consumed and gone.
Exactly. Kafka, however, operates more like a durable distributed log. It's designed to persist messages for a configurable period. This could be hours, days, weeks, or even indefinitely, depending on storage capacity and configuration.
Indefinitely.
Yeah. This fundamentally changes how you can interact with your data streams. It means that new consumer applications can be deployed later and can start reading from the beginning of a topic, effectively replaying historical data. It also allows existing consumers to rewind their position and reprocess data if needed, which is incredibly powerful for debugging, auditing, recovery from bugs, or evolving your data processing logic without losing that historical context.
That idea of being able to replay past events sounds incredibly useful.
Okay.
Like, if you deploy a bug in a consumer, you can fix it and reprocess the affected data range. That's a very different paradigm from messages being transient.
Exactly. It treats the message log as a source of truth. And beyond just storage, Kafka has also been evolving to integrate stream processing capabilities directly within the platform itself.
Oh, like processing the data in Kafka.
Yeah. With libraries like Kafka Streams, which is a client library, or tools like KSQL, which offers a SQL-like interface on top of streams, you can perform real-time data transformations, aggregations, joins between streams, and analysis directly on the messages flowing through Kafka topics.
So less need to pull data out to a separate processing system.
Potentially, yes. It allows you to create continuously updating materialized views of your data directly from the streams and build sophisticated stream processing applications, often without needing a separate dedicated engine like Flink or Spark Streaming, though those are still used too, of course. It really blurs the lines between messaging and data processing, offering powerful new ways to manage and react to data in distributed systems.
This has been incredibly insightful. So just to bring it all together, when I'm thinking about queues versus topics for an interview, I should remember that queues are generally point-to-point, focused on workload distribution, often used for commands or tasks where one worker does the job.
Right, competing consumers pattern. Topics, on the other hand, are a broadcast mechanism, publish-subscribe, ideal for event-driven architectures, where multiple independent services need to be informed of the same event.
Decoupled event notification.
Yeah. And message brokers in general are essential for building reliable, scalable, and fault-tolerant systems by enabling asynchronous communication and providing guarantees like at least once, or maybe exactly once processing, around message delivery, plus features like ordering or transactions depending on the broker. This is definitely foundational knowledge for anyone aiming for a senior software engineering position.
Precisely. Demonstrating a deep understanding of these concepts, being able to articulate the trade-offs between different approaches like queue versus topic, or different broker choices, or consistency levels, and knowing when to apply each pattern is what really differentiates a senior engineer in an interview setting.
So, as you're preparing for those technical interviews, really take the time to understand these concepts inside and out. Think about how you would apply them in different system design scenarios and be ready to discuss the pros and cons, the nuances. Definitely. And on that note, here is maybe a final thought to consider as you continue your preparation. Given the inherent trade-offs we know exist in distributed systems, think CAP theorem, consistency versus availability, and considering that message brokers are a key part of these systems, how would you approach designing a messaging infrastructure that needs to balance strong guaranteed delivery with, say, extremely high throughput and low latency requirements? What are some of the key architectural choices and potential bottlenecks or challenges you might anticipate?
That's a fantastic question to really make you think critically about the practical trade-offs. We also highly recommend diving into the specifics of the documentation for the message brokers that are most relevant to your experience or the types of systems you're interviewing for. Know your tools. Thanks for joining us for this deep dive into message brokers.
My pleasure. Good luck with the interviews.